The universe began with a bang, but that famous story is missing its first page. In the very first sliver of a second, something far more dramatic occurred. An event so violent and strange it defies easy imagination. This was the cosmic inflation era, the universe's most explosive and mysterious growth spurt. In less time than it takes light to cross a single atom, our entire cosmos expanded from a speck smaller than a proton to a volume larger than everything we can see today. That fraction of a second set the stage for every galaxy, star, and planet that would ever form. By the end of this journey, you will possess a deeper understanding of the 25 profound mysteries locked within that primordial instant, the cosmic detective story that defines our very existence. We will explore what could have triggered such a frenzy, whether our universe is alone in a frothing multiverse, and how quantum ghosts were stretched into the seeds of all life. What do you believe is the ultimate question about our beginnings? The biggest mystery of all is the first one. What turned the lights on? What triggered inflation in the first place? To understand the possible answer, we need to visit a strange state of reality called a false vacuum. Think of the universe like a ball resting in a valley. That valley represents a stable, low-energy state, the kind of calm cosmos we live in today. But physicists propose that in the very beginning, the universe was not in this valley. It was perched high up on a plateau, a precarious high-energy state known as a false vacuum. This state was unstable, like a ball balanced perfectly on the tip of a mountain. It only looked stable. The tiniest nudge, a random quantum fluctuation, could send it rolling, and that is where our hypothetical hero, the inflatoned field, comes in. This is not a particle, but a field of energy that permeated all of space. Picture it as the landscape itself. The inflatoned field held the universe in that false vacuum state, and its energy is what drove the insane expansion. For a fleeting moment, that field held the ball perfectly still on the plateau. Then something gave it that nudge. The field began to decay or roll down the hill, as physicists say. As it rolled, it released its colossal stored energy. That energy did not create matter or light yet. Instead, it fueled the exponential stretching of space itself. This is the critical shift in our story. The Big Bang, the hot, dense fireball we often think of as the beginning, was not the start. It was the spectacular finale of inflation. When the inflatoned field finally reached the bottom of the valley, when that false vacuum decayed into our true, stable vacuum, all that inflationary energy was dumped into the cosmos in an instant. It filled the newly stretched space with a seething plasma of particles and radiation. That moment, the end of inflation, is what we call the hot Big Bang. So the trigger question remains. What was the initial nudge? Was it an inevitable quantum tick, a random event in a frothing pre-inflationary soup, or the influence of something from a prior cosmic cycle? We do not know. The switch was flipped in darkness, leaving us to trace its consequences from the brilliant aftermath. That final burst of energy created a cosmos of stunning order. But this presents our second great mystery. How did it all start so smoothly? To appreciate the depth of this question, we must rewind to the moment just before inflation began. The universe, however tiny, should have been a chaotic, crumpled mess. Think of space itself as a sheet of paper. You could crumple it into a tight ball covered in sharp creases and folds. Or you could curve it gently like a bowl, or you could lay it perfectly flat. The geometry of our universe, according to Einstein's theories, is dictated by its density. Too much matter and energy, and space curves in on itself like a sphere, eventually collapsing. Too little, and it curves outward like a saddle, flying apart forever. The precise balance for a flat Euclidean geometry is incredibly delicate. For the universe to be as flat as we observe it to be today, some 14 billion years after the Big Bang, its initial conditions had to be fine-tuned to an accuracy of 1 part in 10 to the power of 60. That is a 1 followed by 60 zeros. It is like balancing a pencil on its tip for the entire age of the cosmos. This is the flatness problem. Why was the baby universe born in such a perfectly balanced flat state? The classical Big Bang theory had no answer. It was simply an unexplained, miraculous starting condition, but inflation provides an elegant solution. It acts as a cosmic iron. Imagine that tiny, pre-inflationary universe, whatever its initial shape. It could have been wildly curved, a crumpled ball of space-time. Now inflate it, take that tiny patch and stretch it by a factor of trillions upon trillions. What happens to the wrinkles if you take a small, wrinkled section of a balloon's surface and blow the balloon up to the size of the Earth? That tiny patch will appear perfectly smooth and flat to anyone standing on it. The colossal stretching of inflation does exactly this to space-time. It smooths out any initial curvature, ironing it into the flat geometry we measure. This same process solves the related horizon problem. The puzzle of why opposite sides of the observable universe have the same temperature even though light has not had enough time to travel between them since the Big Bang. The answer is that those distant regions were once intimately close together in that tiny, pre-inflationary patch. Inflation then blew them apart, but they started with the same conditions. So while inflation beautifully explains how we got a smooth, flat universe from almost any starting point, it quietly reframes the mystery. We no longer ask why the initial conditions were perfectly flat. Instead, we ask, what were those initial conditions? What did that tiny, primordial patch of reality look like before the stretching began? Was it a quantum foam, a remnant of a previous cosmos, or something beyond our current physics? Inflation hides the answer, stretching the original signature of creation so thin we may never read it. This staggering expansion forces us to confront a paradox of cosmic proportions. Where did all that energy come from? To inflate the universe from a subatomic speck to a volume larger than our observable cosmos in less than a blink, an unfathomable amount of energy had to be summoned. It seems like the ultimate free lunch, a blatant violation of one of physics' most sacred laws, the conservation of energy. Energy cannot be created or destroyed, only transformed. So how did the universe pull this off? The answer lies in a strange and profound feature of gravity itself. In Einstein's general relativity, the gravitational field can carry negative energy. Think of it this way. Imagine you have a stone and you lift it high above the ground. You have done work. You have added positive energy to the stone by giving it gravitational potential energy. Now let it fall. As it falls, that positive energy is converted into kinetic energy, the energy of motion. But from the perspective of the gravitational field, something else happens. When the stone was up high, the gravitational field was in a higher energy state. When the stone falls, the field relaxes into a lower energy state. The energy the field loses is negative energy. This is the cosmic ledger that balances the books during inflation. The inflattened field driving the expansion possessed a tremendous amount of positive energy. This positive energy went into the furious stretching of space itself. But simultaneously, the gravitational field associated with this new, expanding space acquired an equally tremendous amount of negative gravitational energy. The books balanced perfectly. The total energy of the universe could have remained zero or very close to it throughout the entire process. The positive energy of matter and radiation we see all around us, everything that makes up stars and planets and us, could be perfectly offset by the negative energy stored in the gravitational field that binds the cosmos together. It is a breathtaking idea. The entire universe, in its most fundamental accounting, may have cost nothing. The sheer scale of this energy transformation is beyond human comprehension. We are talking about the creation of all space and the seed of all matter from what might have been a perfect balance of positive and negative. a quantum fluctuation writ large across the canvas of reality. This leads us to a haunting and beautiful possibility. Our magnificent universe, in all its splendor and complexity, could be the ultimate something that emerged from nothing. But this elegant solution to the energy problem opens a door to an even more dizzying possibility. If inflation could start from a quantum seed and stretch reality into everything we see, what is to stop it from happening more than once? This leads us to the fourth profound mystery. Did inflation itself have a beginning, or could it be eternal, reaching infinitely back into the past? Some models of the inflated field suggest a startling answer known as eternal inflation. Imagine the inflated field not as a single smooth hill, but as a vast, rocky, and uneven landscape. In most regions, the field would quickly roll down into a valley, ending inflation and creating a hot Big Bang universe like our own. But the landscape could have plateaus or even upward slopes. In certain patches, quantum fluctuations could actually push the inflated field up the energy hill, not down. In those regions, the false vacuum state persists, and inflation keeps raging on, stretching space even faster than the surrounding areas. In this picture, inflation is not a single event that happened and stopped. It is a self-replicating, endless process. The eternally inflating background is like a boiling pot of water, a frothing sea of space-time expanding at an insane rate. But within that foam, bubbles spontaneously form. Each bubble is a region where, by random quantum chance, the inflated field has finally decayed, inflation has ended, and a stable universe like ours is born. Our entire cosmos, with all its hundreds of billions of galaxies, would be just one such bubble, one pocket universe in an infinite, ever-growing multiverse. The implications of this idea are staggering. If eternal inflation is true, then our Big Bang was not the absolute beginning. It was a local phase transition within an infinite, older metacosmos. There was no first bubble. The process has simply been happening forever, with no start and no end, continuously spawning new universes, each with potentially different laws of physics, different constants, even different numbers of spatial dimensions. Our universe's particular settings, the force strengths and particle masses that allow for atoms, stars, and life, would not be a finely tuned miracle. They would be a cosmic accident, one random draw from an infinite lottery of possibilities. We just happened to live in a bubble where the numbers allowed us to exist. This is a hypothesis that sits at the very edge of science, as it makes predictions about regions of reality forever beyond our observational reach. Yet, it emerges naturally from the mathematics of inflation itself. It forces us to confront a humbling scale. We are not just living in a universe that grew from a speck. We may be living in a single bubble, adrift in a frothy, infinite ocean of other universes, a cosmic foam where the act of creation is not a singular past event but an ongoing, eternal fire. But if inflation is a runaway process, how did it ever stop? This is the fifth great mystery, known to cosmologists as the graceful exit problem. For our universe to exist, inflation could not rage on forever. It had to end, and it had to end in a very specific, finely tuned way. Think of the inflated field as a ball rolling down a hill. The steepness of the hill and the shape of the valley at the bottom determine everything. If the hill is too steep, the ball rolls down too quickly. Inflation ends almost instantly before space has been stretched enough to solve the flatness and horizon problems. The universe would remain small, crumpled, and inhospitable. If the hill is too shallow, the ball rolls down too slowly. Inflation lasts too long, stretching space so thin that all structure is diluted away into a near-perfect vacuum, leaving behind a cold, empty, and dark cosmos. Somehow, the inflated field in our universe found a perfect middle path. It rolled down its energy hill at just the right pace, inflating the universe by the colossal factor needed to make it smooth and flat, but then it reached the bottom and stopped. This moment of transition is called reheating, and it is one of the most violent and creative events in cosmic history. When the inflattened field settled into its stable state, it did not just sit quietly. All that pent-up energy, the fuel that had been driving the expansion of space itself, had to go somewhere. In a final, spectacular burst, the inflattened field decayed. Imagine a vast, silent field of energy suddenly vibrating, shaking itself apart. From this frenzied oscillation, particles began to erupt into existence. Out of the cold, empty geometry of inflated space, a seething, ultra-hot plasma of quarks, electrons, photons, and other fundamental particles was born. This was not a gentle warming, it was the instantaneous ignition of the hot Big Bang fireball. The entire observable universe was filled with this blindingly hot, dense soup in a flash. The smoothness of this process is absolutely critical. If reheating had been patchy or uneven, if some regions converted their energy more efficiently than others, the newborn universe would have been lumpy and inconsistent from the start. Such irregularities would have grown under gravity, potentially collapsing the cosmos into black holes or tearing it apart before stars could ever form. Yet the cosmic microwave background shows us a universe that was remarkably uniform. This tells us that reheating must have been an incredibly efficient and widespread event, a synchronized cosmic transformation that happened almost everywhere at once. The fine-tuning here is exquisite. The shape of the inflattened field's potential energy hill, the rate of its roll, and the efficiency of its decay all had to align with precision to produce the stable, structured universe we call home. We are left wondering, was this perfect exit plan written into the laws of physics from the start, or are we simply living in one rare bubble where, by chance, everything went exactly right? The flawless ignition of the hot Big Bang rests entirely on the behavior of one theoretical entity. But what if the architect of our universe is a ghost? This brings us to the sixth mystery, the search for the inflattened field itself. Is it real, or is it a mathematical placeholder, a convenient fiction that explains the data but has no physical reality? To answer that, we need to understand what a field actually is. Think of the universe not as a collection of isolated particles, but as an ocean. This ocean is filled with different kinds of fields, invisible entities that stretch everywhere. An electron is not just a tiny ball, it is a localized ripple in the electron field. Light is a wave in the electromagnetic field. The Higgs boson, discovered in 2012, is a ripple in the Higgs field, which gives other particles their mass. The inflattened field is proposed to be another such ocean, a fundamental ingredient of reality that just happened to have the right properties to drive that explosive early expansion. The critical question is whether this inflatten is something entirely new and fundamental, a cousin to the Higgs field, or if it is simply a combination of fields we already know about, interacting in a way we do not yet understand. Its proposed behavior is incredibly specific. It had to be a scalar field, meaning it had a value at every point in space but no direction, like a temperature reading. It had to possess a very particular shape of potential energy, that hill we discussed, to drive a slow roll and then a rapid decay. Finding any direct evidence for this field is one of the greatest challenges in cosmology. Since the field decayed and transformed itself away at the end of inflation, we cannot detect it directly today. We are left searching for its fingerprints, the indelible marks it left on the cosmos as it worked. The most promising signature is primordial gravitational waves. During inflation, the violent stretching of space-time should have created ripples in the very fabric of the universe, gravitational waves that have been propagating through the cosmos ever since. These are not waves in water or air, they are literal stretches and squeezes of space itself. If we could detect these ancient ripples, it would be a smoking gun for the inflationary process and tell us something profound about the inflattened field's energy scale. Another clue lies in the detailed patterns of the cosmic microwave background. The minute temperature variations we see are believed to be the amplified quantum fluctuations of the inflattened field itself, frozen in when inflation ended. By studying the statistical properties of these fluctuations like a cosmic fingerprint, physicists can test different models of the inflatten's potential energy hill. So far, the inflatten remains a brilliant theoretical construct, the leading explanation that ties together a host of cosmic puzzles. But until we catch one of its predicted echoes from the dawn of time, it remains a shadowy figure in our origin story, the unseen sculptor whose existence we infer only from the shape of its creation. The hunt for these ancient echoes has become one of cosmology's greatest quests. This is the seventh mystery, the search for primordial gravitational waves, the definitive smoking gun of inflation. To understand why they are so crucial, picture the infant universe during that explosive growth spurt. Space-time itself was not being passively stretched. It was being violently agitated, shaken by the immense energy of the inflattened field. Just as a boat churning through water creates ripples, inflation churning through the fabric of reality should have created ripples in space-time itself. These are gravitational waves, but not from colliding black holes or neutron stars. These would be the first waves, generated when the universe was less than a trillionth of a second old, and then stretched to cosmic scales by inflation itself. They would be a fossil imprint of the universe's most violent moment. The challenge is finding them. These waves are incredibly faint, a whisper buried under 14 billion years of cosmic noise. But cosmologists have a brilliant plan to listen for them. They are not building a giant microphone. They are using the oldest light in the universe as a screen. The cosmic microwave background, that afterglow from the hot Big Bang, is our canvas. When primordial gravitational waves pass through space, they do something extraordinary. They very slightly stretch and squeeze space itself in a particular twisting pattern. As this distorted space interacted with the hot plasma of the early universe, it would have imprinted a unique signature on the light, a specific type of polarization known as B modes. Think of light as a wave that vibrates in a certain direction. The hot and cold spots of the CMB can create simple polarization patterns like lines radiating from a point. But the twisting effect of gravitational waves creates a curling, pinwheel-like pattern in the polarization, a swirling fingerprint that is very difficult to produce by any other means. Finding these B modes in the CMB would be like finding the artist's signature on the masterpiece of creation. The excitement around this possibility reached a fever pitch in 2014. A team using a telescope at the South Pole called BICEP2 made a stunning announcement. They believed they had detected these primordial B modes. The scientific community and the world held its breath. This was it, the Nobel Prize-level confirmation of inflation, a direct glimpse into the universe's first moment. But the celebration was short-lived. Further analysis, crucially involving data from the European Space Agency's Planck satellite, revealed a devastating complication. The signal BICEP2 detected could be entirely explained by something much more mundane, cosmic dust within our own Milky Way galaxy. Interstellar dust, when aligned by magnetic fields, can also polarize light and mimic the swirling B-mode pattern. The initial announcement was a sobering lesson in the extreme difficulty of this hunt. You are trying to find a whisper from the beginning of time, a signal buried under the static of our own galactic backyard. The search continues with more sensitive experiments, better dust mapping, and relentless patience. The stakes could not be higher. A confirmed detection would not just prove inflation happened, it would tell us the energy scale at which it occurred, giving us vital clues about the inflattened field itself. It would be a direct message from the cosmic inflation era, a tremor in space-time that has traveled to us from the very edge of reality. The hunt for primordial gravitational waves is a search for a whisper, but the cosmic microwave background also holds a shout, a strange and silent scream from the depths of space. In the all-sky map of this ancient light, there is a feature that simply does not fit. It is known as the cold spot, a vast region of the sky where the temperature of the microwave background is significantly lower than the surrounding average. This is not a tiny statistical blip. The cold spot is enormous, spanning a diameter of about 10 degrees in the sky, which corresponds to a structure billions of light years across if it is truly a primordial feature. Its existence challenges our understanding of cosmic uniformity and whispers of a far more dramatic possibility. Could this be a bruise, a scar from a collision with another universe? This idea emerges directly from the concept of eternal inflation and the multiverse. In that frothing sea of eternally inflating space, our universe is one bubble among infinite others. These bubbles are not static, they nucleate, expand, and sometimes they can collide. If another bubble universe brushed against ours during the very early stages of its inflation, the impact would have been catastrophic on a cosmic scale. The collision would have deposited an immense amount of energy into the wall of our bubble, but that energy would not have stayed localized. As inflation continued to stretch our universe, that collision scar would have been smeared across an enormous volume of space. By the time the cosmic microwave background was emitted, that region would have been left with a distinct signature, a large circular area where the physics of reheating was slightly different, resulting in a noticeable cold spot in the afterglow. It is a breathtaking thought. That subtle chill in the microwave sky could be the fossilized imprint of another reality, a neighboring cosmos that touched our own in the first instance of creation. The cold spot would then be our first empirical evidence for a multiverse, a window punched through the wall of our observable universe. Yet, extraordinary claims require extraordinary evidence, and cosmologists have proposed more conventional, if still fascinating, explanations. The leading alternative is that the cold spot is not a primordial feature at all, but a shadow cast by a later structure. It could be caused by a vast cosmic void, an enormous region of space that is surprisingly empty of galaxies and galaxy clusters. If such a void lies between us and the surface of last scattering, the light from the CMB passing through it would lose a tiny amount of energy due to a subtle effect called the integrated Sachs-Wolfe effect. Think of it as light climbing out of a gravitational well. As photons from the hot, dense early universe stream toward us, they pass through regions of varying density. If they pass through a large, relatively empty void, a region of weaker gravity, they actually gain a tiny bit of energy as they climb out. This makes the CMB appear slightly hotter in that direction. Conversely, if they pass through a massive cluster, they lose energy falling in, making the CMB appear colder. The puzzle is that the cold spot is so large and so cold that it would require a void of staggering proportions, one that challenges our models of how structure forms in the universe. Surveys have found some evidence of a sparser region of galaxies in that direction, but whether it is large enough or empty enough to explain the cold spot remains hotly debated. So we are left with a cosmic detective story. Is the cold spot a statistical fluke in an otherwise uniform sky, a trick of the data? Is it the shadow of the largest nothing we have ever seen, a colossal void? Or is it something far more profound, the first tangible evidence that our universe is not alone, that we bear the mark of a long-ago encounter with another reality? The mystery chills the data, inviting us to look deeper into the cold. The cold spot is not the only ghost in the machine of the cosmic microwave background. As our maps of this ancient light have grown more precise, other, even stranger features have emerged, features that seem to whisper of a fundamental crack in our beautiful inflationary story. This brings us to the ninth great mystery, a collection of anomalies so puzzling that cosmologists have given one of them a dramatic name, the axis of evil. Recall that the cornerstone prediction of inflation is a universe that is statistically isotropic. This is a fancy way of saying the cosmos should look the same in every direction. There should be no preferred axis, no cosmic north or south, no special left or right. The hot and cold spots in the microwave background should be scattered randomly across the sky, like the static on an old television set. But when scientists began to analyze the detailed statistical patterns in the CMB data from satellites like WMAP and Planck, they found something unsettling. The largest scale fluctuations, the biggest hot and cold spots, are not arranged randomly. They appear to be aligned along a particular axis in space. It is as if someone drew a faint line through the universe, and the largest structures decided to line up along it. This unexpected alignment is what has been dubbed the axis of evil. The strangeness does not stop there. Another anomaly is known as hemispherical asymmetry. When you divide the sky into two halves, one hemisphere appears to have, on average, slightly larger temperature fluctuations than the other. It is not a dramatic difference, but it is a statistically significant one. It is as if the microwave background is slightly louder, more variable on one side of the sky than the other. This breaks a principle called statistical isotropy even more directly. The universe on its largest observable scales seems to have a preferred side. So what are we to make of these cosmic irregularities? The first and most conservative explanation is that they are simply flukes. We have only one universe to observe, and sometimes in a random distribution, you can get patterns that look significant purely by chance. It is like flipping a coin 100 times and getting a surprising run of 7 heads in a row. It feels meaningful, but it can happen in a truly random sequence. Perhaps we are just seeing a statistical quirk in our particular patch of the cosmos. The second possibility is that these are not primordial at all, but artifacts of our observation. Could something in our own galactic neighborhood, or even in the processing of the immense datasets from space telescopes, be imprinting these subtle patterns? Scientists have scrutinized this possibility relentlessly, accounting for the Milky Way's emissions, the solar system's motion, and countless other foreground effects. While some of the smaller anomalies have been explained away, the largest ones, like the axis of evil and the hemispherical asymmetry, stubbornly persist. This leads to the third and most thrilling possibility. What if these anomalies are not mistakes but messages? What if they are faint echoes from a time before inflation, imprints of a reality that existed when our universe was born? Inflation is supposed to have ironed out all such pre-existing structure, stretching any initial wrinkles to invisibility. But what if inflation did not start from a perfectly symmetric point? What if the tiny seed that inflated was itself slightly lopsided, or had some residual structure from a prior cosmic phase? In that case, inflation would have stretched that initial asymmetry to a cosmic scale, embedding it as a faint, preferred direction in the very fabric of our universe. The axis of evil could then be a fossil, a relic of the universe's true initial conditions, a memory that even inflation's furious stretching could not completely erase. This idea forces us to confront a profound limit of our knowledge. Inflation explains how we got from a tiny, possibly messy beginning to a smooth, flat universe. But it deliberately hides the nature of that beginning from us. These large-scale anomalies are like cracks in that curtain, tiny glimpses of what might lie behind it. They hint that the story of our origins may be more complex, more textured, and perhaps more connected to something beyond our current comprehension. Are we seeing the shadow of a parent universe, or the signature of a quantum birth that was not perfectly uniform? For now, these alignments in the ancient light remain silent sphinxes, guarding secrets from the first moments of everything. Those strange alignments in the ancient sky force a deeper question about our origins. If the largest structures hint at a pre-inflationary world, then what about everything else? What planted the seeds for every galaxy, star, and planet in the cosmos? The answer is one of inflation's greatest triumphs, and it ties directly to the quantum nature of reality itself. The universe began not just smooth, but too smooth. A perfectly uniform soup of hot particles would never have clumped together under gravity. You need tiny imperfections, places that are ever so slightly denser than average, to act as gravitational anchors. For decades, the source of these initial density variations was a profound puzzle. Inflation provided an elegant and breathtaking solution. It pulled them out of the quantum foam. At the subatomic scale, empty space is not empty. It is a seething, frothing sea of virtual particles that wink in and out of existence, a consequence of Heisenberg's uncertainty principle. These are quantum fluctuations, momentary bubbles of something from nothing. In the calm universe of today, these fluctuations are microscopic and fleeting. But during the inflation era, something extraordinary happened. The inflatoned field itself was subject to these same quantum jitters. Its energy density had tiny, random variations from point to point. Normally, such quantum fuzz would be irrelevant, vanishingly small. However, inflation's furious expansion acted like a cosmic amplifier. Imagine a tiny, microscopic ripple on a pond. Now imagine the pond itself suddenly expanding to the size of an ocean in an instant. That tiny ripple would be stretched to a vast, continent-sized wave, frozen into the new, larger geometry. That is precisely what inflation did to the quantum fluctuations in the inflatoned field. As space expanded exponentially, these infinitesimal quantum bumps and dips were stretched across astronomical distances. Where the field had a tiny peak, a bit more energy was locked in. Where it had a dip, a bit less. When inflation ended and reheating occurred, these frozen-in variations in the inflatoned field were translated directly into variations in the density of the hot plasma. Regions that had a little more inflatoned energy became slightly hotter and denser patches. Regions with less energy became slightly cooler, emptier patches. These minute differences, on the order of 1 part in 100,000, became the cosmic blueprint. Gravity then took over. Over hundreds of millions of years, those slightly denser patches pulled in more matter from their surroundings, growing steadily larger. They became the first protogalactic clouds, then galaxies, then clusters of galaxies. The slightly emptier patches evolved into the vast cosmic voids we see today. The entire large-scale structure of the modern universe, a cosmic web of filaments and nodes, was woven from threads of quantum uncertainty magnified to a cosmic scale. This is a staggering connection. The same quantum mechanics that governs the behavior of electrons and photons in a laboratory also wrote the architectural plan for the cosmos. The microscopic and the macroscopic are linked by that brief, violent episode of stretching. Yet this brilliant success hides a deeper layer of mystery. The process of stretching a quantum fluctuation into a classical density seed sits at the uneasy border between quantum mechanics and general relativity, a frontier we call quantum gravity. How exactly does a probabilistic quantum jitter freeze into a definite classical seed? It is as if the act of rapid expansion itself forced the quantum world to make a choice, to commit to a specific configuration that would then dictate the fate of billions of galaxies. We do not fully understand that transition. It suggests that the seeds of all structure were not predetermined, but were chosen at random from a quantum menu of possibilities in that first fraction of a second. Our local universe, with its specific arrangement of galaxy clusters and voids, might be just one random realization. In another region of the cosmos, inflated from a different patch of the quantum foam, the large-scale structure could look entirely different. We are living in a cosmic fingerprint that began as a quantum dice roll, amplified to the grandest scale imaginable. That quantum dice roll, stretched into galaxies, exposes the fundamental flaw in our cosmic story. We have been describing inflation using two magnificent but incompatible rulebooks. On one hand, we have Einstein's general relativity, which masterfully describes gravity as the curvature of space-time on cosmic scales. On the other, we have quantum mechanics, the bizarre and brilliant rulebook for the subatomic world. For nearly a century, these two pillars of modern physics have refused to speak the same language. And inflation, by its very nature, forces them into a direct confrontation. This is the 11th mystery, the quantum gravity conundrum, the single greatest theoretical obstacle to understanding the true beginning. Think of it this way: general relativity paints a smooth, geometric picture of the universe. It sees space-time as a flexible fabric warped by mass and energy. Quantum mechanics, however, reveals a universe that is fundamentally grainy and probabilistic at the tiniest scales. Particles can be in two places at once, and empty space fizzes with temporary particles. These descriptions work perfectly in their own domains. We use quantum mechanics to build computer chips and general relativity to guide GPS satellites. But during the cosmic inflation era, these domains collided. Inflation is thought to have been driven by energies unimaginably close to the Planck scale. This is the ultimate energy frontier, a regime so extreme that the very concepts of smooth space and time break down. At the Planck scale, quantum fluctuations are believed to become so violent that space-time itself should turn into a chaotic, foaming sea. Geometry becomes fuzzy. The smooth fabric of general relativity dissolves into a probabilistic quantum froth. Our current physics has no equations to describe this. It is like trying to use the rules of fluid dynamics to describe the behavior of individual water molecules. We are missing the theory of quantum gravity, a framework that would seamlessly weave together the smooth geometry of relativity with the grainy uncertainty of the quantum world. Without it, our story of inflation's inception is incomplete. We can describe what happened after it started, using a kind of patchwork of the two theories, but we cannot reliably describe the moment it was triggered, or what, if anything, came before. It is the cosmic equivalent of having a detailed film of a tree's growth, but no understanding of how the seed itself formed. Several candidates for this unified theory exist, though they remain unproven. String theory, for instance, proposes that the fundamental building blocks of reality are not point-like particles, but incredibly tiny, vibrating strings. These vibrations give rise to all forces and particles, including the carrier of gravity, the graviton. In this view, the inflation era might be described as a specific dynamic of these strings and higher dimensional membrane. Another approach, loop quantum gravity, suggests space itself is not continuous but woven from tiny, discrete loops, a fabric of finite threads. This leads to a dramatic idea called the Big Bounce, where our expanding universe emerged from the collapse of a previous one, with inflation occurring as space rebounded. These theories are mathematically beautiful and intellectually thrilling, but they make predictions that are currently, and perhaps forever, beyond the reach of our experiments. They operate in a realm of energy we can never hope to recreate in a particle collider. So we are left at a precipice. Inflation is our best story for the universe's early moments, a story that explains so much of what we see. Yet its very first page is written in a language we cannot yet read. The quantum gravity conundrum tells us that to truly understand the birth of our cosmos, we must first solve the deepest puzzle in all of physics. We must discover what space and time actually are when they are probed at the ultimate scale. Until we do, the trigger of inflation remains hidden behind a veil of quantum uncertainty, a mystery written in the fundamental code of reality itself. Our cosmic fingerprint, born from a quantum dice roll, is vast beyond comprehension, yet it may be just a single brushstroke on an infinite canvas. This is the 12th mystery, the question of the universe's total size, a direct and staggering consequence of inflation's relentless logic. We talk about the universe all the time, but we must make a crucial distinction. What we can actually see from our tiny vantage point on Earth is the observable universe. It is a sphere centered on us with a radius of about 46.5 billion light-years. This is not the distance light has traveled in 14 billion years, because space itself has been expanding all that time. It is the present-day distance to the most ancient photons we can detect, the edge of our cosmic horizon. Everything within that sphere, hundreds of billions of galaxies, is our local neighborhood. But inflation tells us this is not the whole story, not even close. Remember, inflation took a region smaller than a proton and expanded it to a size far larger than our entire observable universe, all in a fraction of a second. The critical point is this: that initial patch that inflated to become everything we see was just one tiny piece of whatever existed before. And if the conditions for inflation were present in that patch, why wouldn't they be present elsewhere? The simplest models suggest that inflation did not just create our observable bubble, it created space itself on a scale that defies human intuition. Think of it like this: you are standing in a vast, dark field on a foggy night. You have a single, powerful flashlight. The beam of your flashlight illuminates a sphere around you, revealing trees, rocks, and grass. That sphere of light is your observable universe. You can only see what the light has had time to reach, but you know the field extends far beyond that circle of illumination. The total universe is the entire field, in all directions, possibly with no end. Inflation is the process that created not just the patch of ground you are standing on, but the field itself, and it suggests the field is not just large but perhaps truly infinite. If the universe is infinite, then a shocking truth follows. Every possible configuration of matter within the laws of physics must be repeated somewhere. In an infinite cosmos, there is a perfect copy of you, reading a perfect copy of this script on a planet identical to Earth, orbiting a star identical to our Sun, in a galaxy identical to the Milky Way. Not just one copy, but an infinite number of them scattered across the endless expanse. This is not science fiction. It is a logical consequence of infinity and a finite set of quantum possibilities. The idea is humbling and existentially dizzying. Our entire history, every triumph and tragedy, every person who has ever lived, would be just one iteration in an infinite library of variations. Of course, we have no way to ever confirm this. Those other Earths, those other versions of us, lie forever beyond our cosmic horizon, receding from us faster than light can travel due to the continued expansion of space. They are causally disconnected from us, islands in an eternal sea, so we are left with a profound puzzle. Is the universe finite but unimaginably large, a colossal but closed structure? Or is it actually infinite without boundary or end? Our current data favors a flat geometry, and a flat universe can be either finite like the surface of a cylinder or infinite like an endless plane. The measurements are not precise enough to tell the difference. Inflation pushes our minds toward the infinite, not as a philosophical idea, but as a plausible physical outcome of that primordial stretching. We are forced to accept that everything we know and love, every galaxy in our deepest sky surveys, represents less than a single grain of sand on all the beaches of all the worlds that may truly exist. The universe we see is magnificent, but it is almost certainly just our local room in a mansion of impossible proportions, a mansion whose full architecture we will never map. The sheer scale of an infinite cosmos makes the idea of other bubble universes feel abstract and distant. Yet the mathematics of eternal inflation suggests these separate worlds are not always isolated. In the chaotic foam of eternally inflating space, new bubbles are constantly nucleating and expanding. Sometimes they expand into each other. If our universe, in its earliest moments of inflation, was brushed by another bubble, the collision would have been an event of unimaginable violence. Two separate realities, each with their own potentially different laws of physics, would have slammed together at nearly the speed of light. The energy released at that boundary would have been staggering, a cosmic shockwave rippling through the newborn fabric of our cosmos. But here is the key point: inflation did not stop immediately. That collision scar, that bruise on our infant universe, would have been caught in the ongoing exponential expansion. Just like a tiny ink stain on a balloon that is then blown up to the size of a building, the collision mark would have been stretched to an enormous size. By the time inflation ended and the cosmic microwave background was emitted, that bruise would have been imprinted on the sky as a distinct circular feature. It would not be a random hot or cold spot, but a nearly perfect ring of temperature variation, a bullseye in the ancient light. This is the ultimate cosmic detective work. Scientists have been meticulously scanning the detailed maps from the Planck satellite and other observatories, searching for these exact patterns, these circular anomalies that cannot be easily explained by standard inflationary fluctuations or later structures like galaxy clusters. They are looking for the fingerprint of a sibling universe. Finding such a ring would be revolutionary. It would be direct, observational evidence for the multiverse. It would tell us that our universe is not alone, that it bears the scars of a traumatic encounter from its infancy. The properties of the ring, its size, and the temperature difference across it could even tell us something about the other universe that hit us, perhaps hinting at the energy of its inflattened field or the timing of its own birth. Of course, the search is phenomenally difficult. The sky is full of circular features from other causes, like sound waves in the early plasma or the imprint of massive galaxy clusters warping light, an effect called gravitational lensing. Distinguishing a true bubble collision signature from these imposters requires incredibly precise statistical analysis. So far, no definitive, uncontroversial collision ring has been found. Some intriguing candidates have been put forward over the years, circles in the data that seem slightly too perfect, but each time further analysis has shown they could still be statistical flukes in the complex, noisy map of the microwave background. Yet the search continues because the prize is so profound. We are not just looking for an anomaly in the data, we are looking for a message from outside our universe. A confirmed collision ring would be a crack in the wall of our cosmic isolation, proof that our reality is just one bubble in a frothing, eternal sea of creation. It would mean the story of our origins includes a chapter we never dared to believe we could read, a chapter written in the circular bruises of a long-ago impact with another world entirely. The search for a collision ring is a hunt for evidence from outside our universe. Yet some of inflation's deepest puzzles might find their answers not in other dimensions, but in the hidden architecture of our own. This brings us to the 14th mystery, a profound link between the weakness of gravity and the fury of the cosmos's first moment. It is called the hierarchy problem, and it asks a deceptively simple question. Why is gravity so incredibly feeble? Consider a small magnet holding a paper clip to your refrigerator. That tiny magnet, using the electromagnetic force, is effortlessly defeating the gravitational pull of the entire Earth. Gravity is weaker than the other fundamental forces by a factor of a trillion. This is not just a curiosity, it is a glaring imbalance in the laws of physics. The masses of particles like the Higgs boson, which gives other particles their mass, are extraordinarily sensitive to quantum corrections from all other forces. Left unchecked, these quantum effects should drive the Higgs mass, and therefore the scale of the weak force up to the Planck scale, making it trillions of times heavier than it is. Something must be protecting it, keeping the world of atoms and chemistry stable. Proposed solutions often involve new physics like supersymmetry, which posits a shadow partner for every known particle to cancel out these quantum corrections. But here is where cosmic inflation enters the story. The energy scale at which inflation occurred is thought to be only a few orders of magnitude below the Planck scale itself. This means the physics that drove inflation was operating in the same extreme realm where the hierarchy problem becomes acute. Could they be two sides of the same coin? Some compelling models suggest yes. Imagine that the inflattened field itself is connected to the Higgs field, the field that gives particles mass. In certain theories, particularly those involving extra dimensions of space, the same mechanism that explains why gravity appears weak to us could also explain the dynamics of inflation. The idea is that gravity is not inherently weak. Its strength is diluted because it can leak into extra, compact spatial dimensions that are curled up at scales a billion times smaller than an atom. What we feel in our three-dimensional world is just a faint shadow of gravity's full strength. Inflation, in this picture, could be the result of our three-dimensional universe settling into its stable configuration within this higher dimensional landscape. The colossal energy released during that settling process could have fueled the exponential expansion we call inflation. In one sweeping framework, the staggering weakness of gravity and the violent expansion of the early universe are linked, both emerging from the geometry of hidden dimensions. Other models use supersymmetry not just to stabilize particle masses, but to naturally provide a candidate for the inflattened field itself. A specific superpartner particle could have the exact properties needed for that slow roll down the energy hill. This creates an elegant, if speculative, unity. The same new physics that solves the particle physics puzzle of mass also solves the cosmological puzzle of creation. The connection is breathtaking. It suggests that the answer to why you do not float off into space when you jump is intimately tied to the mechanism that blew up the universe from a quantum speck. The physics of the very small, the realm of trembling fields and hidden dimensions, may have written the script for the very large, determining the fate of galaxies before a single star was born. This link remains theoretical, a beautiful possibility written in the mathematics of candidate theories. Yet it offers a powerful hope that by peering back to the inflation era with ever more sensitive probes, we might not just be learning about the cosmos's birth. We might be stumbling upon the key to the final unification of all forces, a theory of everything, etched into the first flash of existence. The profound link between gravity's weakness and inflation's energy hints at an even deeper cosmic balancing act. This brings us to the 15th mystery, a numerical discrepancy so vast it is often called the worst prediction in the history of physics, the cosmological constant problem. It is the story of a vacuum energy that refused to vanish, a ghost from the inflation era that still haunts the cosmos today. To understand it, we must revisit the idea of the vacuum. In quantum field theory, empty space is not truly empty. It is a seething sea of virtual particles that constantly flicker in and out of existence. All this quantum jitterbugging gives the vacuum an intrinsic energy, a background hum to the universe. This is vacuum energy, and according to Einstein's equations, it should act as a cosmological constant, a force that pushes space apart. During the cosmic inflation era, the vacuum energy associated with the inflattened field was colossal. It was the engine of the expansion, a titanic pressure that stretched the fabric of reality. But then, at the end of inflation, that energy was supposed to vanish. The inflattened field decayed, dumping all its energy into creating particles, and the vacuum energy should have dropped to zero, leaving behind a calm, empty space. That is not what happened. Observations of distant supernova and the cosmic microwave background in the late 1990s revealed a shocking truth. The expansion of the universe is not slowing down as everyone expected. It is accelerating. Something is pushing galaxies apart from one another at an ever-increasing rate. That something is what we now call dark energy, and the simplest explanation for it is a cosmological constant, a tiny, persistent vacuum energy that never went away. Here lies the problem of impossible numbers. When physicists try to calculate the expected value of this vacuum energy from known quantum fields, they get an answer that is wrong by a factor of 10 to the power of 120. That is a 1 followed by 120 zeros. It is the largest mismatch between theory and observation in all of science. To say the predicted value is too large is a cosmic understatement. The calculation suggests a vacuum energy so immense that the universe should have ripped itself apart in a fraction of a second after the Big Bang, preventing any atoms, stars, or life from ever forming. Yet the value we actually measure is incredibly small, but crucially not zero. It is just enough to drive the observed acceleration, a faint whisper compared to the scream of inflationary energy. This is the ultimate fine-tuning problem. Why did the vacuum energy drop from an unimaginably huge value during inflation to an almost but not exactly zero value today? It is as if the universe performed a calculation with 120 decimal places of precision, landing on a number that allows for galaxies and life rather than a featureless void or a chaotic shredding. The connection to inflation is profound. The same mechanism that drained the inflationary vacuum energy had to leave behind this infinitesimal remnant. Some theories suggest an unknown symmetry or a cancellation mechanism, where positive and negative contributions from different fields almost perfectly balance, leaving only this tiny residue. Others propose that dark energy is not a constant at all, but a dynamic field similar to the inflaton that is slowly evolving. This would mean the acceleration we see is not a permanent feature of the cosmos, but a phase we are currently passing through. The most haunting possibility is tied to the multiverse. In an eternally inflating landscape spawning infinite bubbles, each universe could have a randomly selected value for its cosmological constant. In the overwhelming majority of those universes, the value is enormous, leading to a rapid, sterile expansion. Only in extremely rare bubbles like ours does the constant fall within the narrow window that allows for structure and life. We exist, therefore we observe this improbably small number. This is the anthropic explanation, and while it offers a kind of answer, it moves the mystery from physics to statistics, leaving many scientists unsatisfied. The cosmological constant problem is a direct bridge between the universe's first instant and its ultimate fate. The same vacuum energy that once blew up the cosmos is now, in a vastly diluted form, determining how it will end. It is a reminder that the story written in the inflation era is not over. Its final chapter, written in the faint push of dark energy, is still being composed, and we are here to read it, wondering why the numbers align just so. The haunting fine-tuning of the cosmological constant forces us to question the very framework that predicts it. While cosmic inflation is the dominant story, the one told in textbooks and press releases, it is crucial to remember it is not the only story ever written. Competing theories of the very early universe exist, each offering a different prologue to the cosmos we see today. One of the most compelling alternatives is the Big Bounce, a central idea in some models of loop quantum gravity. This theory rejects the idea of a singular beginning from nothing. Instead, it proposes an eternal cosmic cycle. In this view, our expanding universe is the rebound from a previous phase of cosmic contraction. A prior universe, perhaps similar to our own, eventually collapsed under its own gravity. But instead of crushing down to an infinitely dense point, quantum gravity effects at the Planck scale create a tremendous repulsive force, like a cosmic spring reaching maximum compression and then pushing back. That repulsive bounce is what we experience as the Big Bang. In this model, there is no need for a separate inflation field. The bounce itself, driven by quantum geometry, produces a rapid, but not necessarily exponential, expansion that can naturally solve the flatness and horizon problems. The smoothing and flattening are achieved not by a brief, violent stretch, but by the immense dilution and entropy generated over an incredibly long contracting phase that preceded the bounce. The universe enters its expanding phase already smooth and flat because it was stretched and homogenized during the long collapse of its predecessor. Another class of ideas falls under emergent universe scenarios. These models propose a universe with no beginning in time at all. The cosmos exists eternally in a static or nearly static state. Then, through a quantum phase transition, it enters an expanding hot Big Bang phase. Imagine a ball resting perfectly still in a shallow depression. A random quantum fluctuation could, over an immense period, nudge it out, sending it rolling into a steep valley, triggering expansion. In such models, the universe could have existed in a quiet, cold, and condensed state for an eternity before something sparked it into the dynamic cosmos we know. So how do these competitors tackle the key puzzles? For the horizon problem, the Big Bounce uses the long contraction phase to allow different regions to communicate and thermalize before the bounce occurs. An emergent universe existing forever in a small state also has infinite time for temperature to equalize. For the flatness problem, the cyclic model relies on the dynamics of each cycle to drive the geometry toward flatness over many iterations, while some emergent scenarios build flatness into the initial eternal state. The critical point is this: each theory makes different, testable predictions. Inflation predicts a specific pattern of primordial gravitational waves and a nearly scale invariant spectrum of density fluctuations which we largely observe. The Big Bounce, depending on the model, might predict a detectable suppression of the largest scale fluctuations in the CMB, a signature of the pre-bounce contraction. An emergent universe might leave no imprint of a beginning at all. The existence of these alternatives is not a weakness of cosmology, but its greatest strength. It reminds us that inflation, for all its explanatory power, remains a paradigm, not a proven fact. The mysteries we have explored, from the trigger to the multiverse to the cosmological constant, are the open questions that keep scientists searching. They are the cracks where new light might shine through, revealing that our origin story may be even stranger and more wonderful than we currently dare to believe. That lingering question of fine-tuning points to an even deeper existential puzzle. Why does anything exist at all? More specifically, why is the universe made of matter? This is the 17th mystery, the puzzle of baryogenesis, and its solution may be hidden in the extreme physics of the inflation era. The laws of physics, as we understand them, show a profound symmetry between matter and antimatter. For every particle, there is an antiparticle with opposite charge. When they meet, they annihilate in a flash of pure energy. In the fiery forge of the Big Bang, energy should have condensed into equal numbers of particles and antiparticles. As the universe cooled, all those matter-antimatter pairs should have found each other and mutually destroyed, leaving behind a cosmos filled with nothing but light, a vast, eternal, and empty glow. Yet here we are, made of atoms, in a universe dominated by stars and galaxies built from matter. Somehow, in that first second, an almost imperceptible imbalance was created. For every billion antimatter particles, there were 1,000,000,001 matter particles. That 1 in a billion excess is all that survived the great annihilation. Everything we see is the ash from that near-total cancellation. The question is, what broke the perfect symmetry? The answer requires 3 ingredients, conditions first outlined by the physicist Andrei Sakharov. The universe must have experienced a departure from thermal equilibrium. It must have contained processes that violate both charge conjugation and charge parity symmetry, and it must have allowed for baryon number violation. These sound abstract, but they describe a very specific kind of cosmic environment. A hot, uniform soup in perfect balance would never generate an asymmetry. You need a dramatic, out-of-balance event to push the system in one direction. You need laws of physics that treat matter and antimatter slightly differently. And you need a way to change the net number of matter particles, something normally forbidden. The end of the cosmic inflation era provided the perfect, catastrophic stage for all 3. Reheating, that moment when the inflattened field decayed and ignited the hot Big Bang, was the ultimate departure from equilibrium. It was not a gentle warming, but a violent, non-thermal process, a sudden injection of energy that could have triggered the right particle interactions. Furthermore, the energy scales involved were unimaginably high, trillions of times beyond what our largest particle colliders can reach. At those energies, new particles and forces predicted by grand unified theories could have been active. These theories naturally include processes that violate the symmetry between matter and antimatter, and that allow the total number of baryons, the building blocks of atomic nuclei, to change. One elegant idea is leptogenesis. In this scenario, the decay of extremely heavy, sterile neutrinos in the early universe would have produced a tiny excess of ordinary matter over antimatter. These heavy neutrinos are themselves relics from a grand unified epoch, and their decay would have been influenced by the chaotic, out-of-equilibrium conditions of reheating. The asymmetry created in leptons, particles like electrons and neutrinos, could then have been transferred into the baryon asymmetry we see today through subtle electroweak processes. What makes this a direct mystery of the inflation era is the intimate link. The energy scale of inflation is tantalizingly close to the energy scale where these grand unified physics and heavy neutrinos would have operated. The inflatoned field's decay did not just create a hot soup, it may have populated the universe with these exotic, asymmetry-generating particles. The violent, non-thermal nature of reheating provided the essential off-balance condition to make the process efficient. In a very real sense, the origin of every atom in your body may be traced back to a quantum process that occurred in the first split second after inflation ended. A fleeting moment when the laws of physics tilted the cosmic scales ever so slightly in favor of existence. We are here because the universe's most explosive growth spurt created the perfect conditions to break its own perfect symmetry, leaving behind a precious residue of something rather than nothing. That precious residue of matter forces us to stare into the ultimate abyss. If inflation set the stage, what set the stage for inflation? Our journey backward through time has brought us to the precipice of the 18th mystery, a question that may forever linger at the very edge of human knowledge. What, if anything, existed before the cosmic inflation era? Our current laws of physics offer no guide here. The equations of general relativity, when wound back to the moment of infinite density, produce a singularity, a point where mathematics fails and reality becomes undefined. Inflation was proposed to avoid that initial singularity, to give us a sensible, physics-driven story for the universe's first measurable moments. But it does not necessarily erase the question of a beginning, it merely pushes it back one step. What was the initial condition of that tiny patch of space-time that then inflated? One profound possibility is that the universe truly began from nothing. Not an empty void, but a literal absence of space, time, and matter. In this view, the entire cosmos could be a quantum fluctuation that simply refused to vanish. According to quantum mechanics, particles can spontaneously appear from empty space, borrowing energy for a fleeting moment before annihilating back into nothingness. If the universe itself is a quantum object, perhaps it too could have tunneled into existence from a state of absolute nothing. The total energy of the universe, as we discussed, may be zero, with positive matter energy balanced by negative gravitational energy. This allows for a startling idea. The universe could be the ultimate free lunch, a quantum fluctuation that grew too large to snap back. In this scenario, there is no before, because time itself emerged with the fluctuation. Another compelling idea returns us to the concept of a cyclic universe, a cosmic heartbeat. Perhaps our inflationary epoch was not the first. A previous universe may have contracted in a big crunch, reaching a state of incredible density before rebounding in a big bounce. The physics of the bounce, governed by a theory of quantum gravity, would have smoothed and reset the cosmos, triggering a new phase of inflation. In this eternal cycle, each universe is both the successor and predecessor of another, an endless sequence with no true beginning or end. There is a before, but it is simply another chapter in an infinite book. A third, even more mind-bending possibility is that the question itself is meaningless. Just as asking what is north of the North Pole is a grammatical trick without a physical answer, asking what came before the beginning of time may be a category error. If time, as we understand it, is a property that emerged from a more fundamental, timeless state, then there simply is no before to discuss. The universe would exist in a kind of eternal, static configuration from which our flowing, expanding reality crystallized. Each of these ideas stretches our language and logic to the breaking point. They operate in a realm where our intuition, built in a world of medium-sized objects and slow speeds, is completely useless. This is why the question of what preceded inflation sits squarely on the border between science and philosophy. Science requires testable predictions, but how can we test a state that existed before the very laws we use to make tests came into being? Any information from a pre-inflationary epoch would have been utterly erased, scrambled, and stretched beyond recognition by the inflationary expansion itself. It is the ultimate cosmic censorship, yet the human drive to ask remains undiminished. This mystery is not just about cosmology, it is about the limits of our understanding. It forces us to confront whether there are questions the universe is fundamentally designed to keep secret, whether the origin of all reality is an event forever shrouded in a veil of unknowability. The search for an answer continues to drive the most theoretical work in physics, pushing toward a theory of quantum gravity that might, one day, allow us to speak meaningfully about that which came before the beginning. For now, we stand at the shore of time, looking back at a horizon we cannot cross, wondering if the ocean of existence has another side, or if we are simply gazing into its infinite, unfathomable source. That ultimate veil of unknowability confronts us with a paradox of numbers. The cosmic inflation era, for all its explanatory power, requires its own kind of miraculous precision. This is the 19th mystery, the fine-tuning of inflation's own parameters, a meta-mystery that asks why the rules of the game were set exactly as they were. Think back to the inflattened field rolling down its energy hill. The steepness of that hill, the mass of the inflaton, how strongly it coupled to other fields, these are not random numbers. They are fundamental parameters, and for inflation to produce a universe like ours, they had to be balanced on a knife's edge. If the inflaton's mass were a tiny bit larger, it would have rolled down the hill too fast. Inflation would have ended before space was stretched enough to become smooth and flat, leaving us with a small, crumpled cosmos. If its mass were a tiny bit smaller, the roll would have been too slow. Inflation would have lasted too long, stretching every quantum seed into irrelevance, leaving behind a vast, cold, and perfectly empty void. The window for a successful, life-permitting inflation is astonishingly narrow. It is as if someone dialed in the values with exquisite care, aiming for the one outcome that allows for galaxies, stars, and planets. So who or what did the dialing? One provocative answer emerges directly from the concept of eternal inflation and the multiverse. If an infinite number of bubble universes are constantly being born, each with randomly selected values for its physical constants and inflation parameters, then most bubbles will be stillborn or sterile. They will inflate too quickly or too slowly, resulting in a cosmos incapable of forming complex structure. But in a vanishingly rare subset of bubbles, purely by random chance, the numbers will fall within that narrow, habitable window. We, of course, find ourselves living in one of those rare bubbles. This line of reasoning is known as the anthropic principle. It states that the observed values of the universe's parameters must be compatible with the existence of observers to measure them. We should not be surprised to find ourselves in a universe capable of producing us, even if such a universe is incredibly unlikely. It is not that the laws were designed for life, but that life can only arise in the places where the lottery of cosmic constants happen to pay out. For some scientists, this is a profound insight, a necessary correction to our cosmic arrogance. It shifts the question from why are the numbers so perfect to what must the larger cosmos be like for us to see these numbers. It turns a mystery of design into a statistical inevitability within a vast multiverse. For others, however, the anthropic principle feels like a philosophical cop-out, a surrender of the scientific quest. It risks making cosmology untestable. If every peculiar feature of our universe can be explained away by saying, "We had to be here to see it," then have we explained anything at all? The challenge is to find predictions that distinguish a finely tuned single universe from a randomly selected one in a multiverse. Some researchers suggest that certain statistical properties of the cosmic microwave background or the distribution of galaxies might carry an imprint of this selection effect. The debate is fierce and fundamental. It strikes at the heart of what science is for. Are we here to discover a single, elegant theory that uniquely predicts our universe, or are we here to map our local neighborhood within an infinite, untidy, and fundamentally random metacosmos? The fine-tuning of inflation's parameters forces this choice upon us. It asks whether the breathtaking precision we see is the signature of a deeper, yet unknown law of physics, a law that mandates these specific values, or simply our address in a cosmic lottery of unimaginable size. The answer will determine not just how we view our origins, but what we believe is ultimately knowable about reality itself. The fine-tuning of inflation's parameters feels like a cosmic riddle we can only observe from a distance. But what if we could bring the dawn of time into the laboratory? The 20th mystery asks a daring question. Can we test inflation in the lab? The energies involved are trillions of times beyond any particle collider we could ever build. We cannot recreate the first moment, yet physicists have begun a brilliant end run around this limitation. They are building analog universes. The key insight is that the mathematical equations describing one physical system can perfectly mirror the equations of another, even if they look nothing alike. The frenzied expansion of space-time and the behavior of certain exotic materials on Earth are described by the same underlying mathematics. This opens the door to tabletop cosmology. One of the most promising arenas is the world of ultra-cold atoms. Scientists can cool a cloud of atoms to a fraction of a degree above absolute zero, a state where quantum behavior dominates. Using precisely tuned lasers, they can create an optical lattice, a kind of egg crate of light that traps the atoms. By suddenly changing the properties of this lattice, researchers can make the system expand in a way that mathematically mimics cosmic inflation. They can watch as quantum fluctuations in the atomic cloud get stretched and frozen, just as primordial quantum jitters were stretched into galaxy seeds. It is a tiny, controlled simulation of creation's first act. Another frontier lies in superconductors and superfluids. These are materials where particles lose their individual identity and act as a single, coherent quantum fluid. Ripples in this fluid can behave exactly like particles and fields in an expanding universe, even creating analogs of Hawking radiation or cosmic horizons. In these chilled, intricate setups, scientists are not recreating the Big Bang. They are creating a functional map, a working model that obeys the same rules. By experimenting on the model, they can probe questions that are untouchable in the cosmos itself. For instance, how exactly does a quantum fluctuation transition into a classical, permanent structure? In the lab, they can tweak parameters, run the experiment thousands of times, and watch the statistics unfold in real time. They can test different models of the inflaton field's potential by engineering different energy landscapes for their atoms. These experiments will never show us a galaxy forming, but they might reveal universal principles about how order emerges from quantum chaos during rapid expansion. They are a testament to human ingenuity, a way to reach across 14 billion years with a laser beam and a vacuum chamber. If successful, tabletop cosmology could turn the greatest mystery of our origins into a reproducible science, letting us hold an echo of Genesis in the palm of our hand. The quest to recreate Genesis in a lab confronts a barrier more fundamental than energy. It is a barrier of information. the 21st mystery asks a startling question borrowed from black hole physics. Did the cosmic inflation era in creating our universe also destroy the very data of its own birth? This is the information paradox of the early universe. To grasp it, we must revisit a crucial moment. Inflation took the quantum fluctuations of the inflatoned field and stretched them into the classical density seeds for galaxies. But in quantum mechanics, information is never truly lost. The complete quantum state of a system with all its probabilities and phases is preserved. This is called unitarity. It is the quantum version of the conservation of information. If you know the complete quantum state of a system now, you can, in principle, use the laws of physics to calculate its state at any point in the past or future. Yet, when a quantum fluctuation is stretched across the cosmos and freezes into a definite hot or cold spot in the microwave background, something profound seems to happen. The infinite possibilities of the quantum wave function collapse into a single classical reality. The delicate quantum information, the phases and correlations that describe the original fluctuation, appears to be erased or at least scrambled beyond recognition. It is as if the universe performed a measurement on itself, choosing one outcome from a menu of probabilities and then threw away the menu. This creates a cosmic version of the black hole information paradox. Black holes, according to classical general relativity, swallow matter and information forever, but quantum mechanics insists that information cannot be destroyed. Physicists like Stephen Hawking wrestled with this for decades, and the prevailing modern view is that information is somehow preserved, perhaps encoded on the black hole's event horizon in a scrambled form. Inflation presents a similar conundrum. The exponential expansion creates a cosmic horizon, a point beyond which events cannot affect us. The quantum details of the pre-inflationary state are pushed beyond that horizon, out of our observable universe forever. The process of converting quantum jitters into classical seeds may have fundamentally scrambled the original quantum data. If this is true, it imposes a brutal limit on cosmology. We can never use the laws of physics to rewind the tape all the way back to the true beginning. The initial quantum state of the universe is not just unknown, it is unknowable in principle. The inflationary expansion acted like a cosmic shredder, taking the pristine quantum data of creation and turning it into the classical, statistical noise we see as the cosmic microwave background. We are left reading the ashes, not the original document. Some theorists propose a more hopeful view. Perhaps the information is not lost but transformed. Just as in the black hole paradox, the information might be imprinted on the cosmic horizon generated during inflation, encoded in the subtle correlations between the hot and cold spots we see in the sky. Decoding that pattern would be a task of unimaginable complexity, like reconstructing a burned book from the pattern of ash. Others suggest that a full theory of quantum gravity will show that unitarity is preserved through the entire inflationary process, meaning the information is still there, woven into the fabric of the universe in a way we do not yet understand. The stakes of this mystery are existential for science. It asks whether the universe's origin is a solvable puzzle or a permanent secret. If information is truly lost, then cosmology becomes an archaeological dig where the most important artifact, the first quantum state, is forever missing. We can describe what happened after the fact, but we can never know why it happened this particular way. The silence from that first moment would be complete, a fundamental horizon on knowledge itself, drawn not by technology, but by the very physics that brought us into being. The silence of creation's first quantum state is not the only missing piece of the cosmic puzzle. Scattered across the vastness of space, another ghostly presence weaves through galaxies and galaxy clusters, a force that should not, by all rights, exist on such a scale. These are primordial magnetic fields, and their origin is one of the most stubborn mysteries in modern cosmology. We find magnetic fields everywhere we look, from planets and stars to entire galaxies, and even the vast spaces between galaxy clusters. They are not just passive features, they play a crucial role in shaping how stars form, how cosmic rays are accelerated, and how galaxies evolve. For decades, astronomers assumed these fields were generated locally, built up slowly over billions of years by the churning motions of ionized gas within galaxies, a process called a dynamo. But there is a problem. To start a dynamo, you need a tiny seed magnetic field to amplify. Where did those initial seeds come from? The answer might lie in the cosmic inflation era. The idea is as elegant as it is challenging. In the calm universe of today, generating a magnetic field requires moving electric charges like a current in a wire. But during inflation, the rules were different. The inflaton field was not just driving expansion, it was interacting with other, more exotic fields predicted by theories beyond the standard model. One possibility involves the coupling of the inflaton to electromagnetic fields. In the violent, exponential stretching of space-time, even a vanishingly small electromagnetic fluctuation could have been caught in the cosmic dragnet and stretched to astronomical proportions. Think of a tiny, microscopic whirlpool in a pond. If you suddenly expanded the pond to the size of an ocean in an instant, that tiny whirlpool would become a vast, continent-spanning gyre. Inflation could have done exactly that to a random magnetic knot in the quantum foam, inflating it from a quantum scale to a scale larger than a galaxy cluster. Another, more exotic mechanism involves a breaking of fundamental symmetries during inflation. Certain theoretical particles, like actions or other pseudo-scalar fields, could have interacted with electromagnetism in a way that converts the energy of the inflaton's rolling motion directly into magnetic fields. It would be like a cosmic generator, with the expansion of space itself turning the crank to produce a persistent, large-scale magnetic field. The appeal of an inflationary origin is clear. It would provide the perfect, ready-made seed fields, already coherent over immense scales, that later galactic dynamos could then amplify into the strong fields we observe today. It would mean the blueprints for galactic magnetism were written in the first trillionth of a second. Yet, for all its theoretical promise, this idea faces tremendous hurdles. The primary challenge is survival. The early universe was a superb conductor, filled with a dense, ionized plasma. In such a plasma, large-scale magnetic fields should quickly dissipate, their energy diffusing away long before galaxies ever formed. For an inflationary magnetic field to survive until the era of galaxy formation, it would need to be incredibly weak but also incredibly coherent, stretched over scales so vast that dissipation could not erase it quickly enough. This is a needle that is very hard to thread with known physics. The search for evidence is equally daunting. If these fields were generated during inflation and still permeate the vast voids between galaxy clusters today, they would be unimaginably faint, billions of times weaker than Earth's magnetic field. Detecting them directly is currently beyond our technological reach. However, they might leave an indirect fingerprint. Such a primordial field would subtly affect the propagation of light across the cosmos, potentially rotating the polarization of light from distant radio galaxies or leaving a signature on the cosmic microwave background. Astronomers are scouring these ancient signals for any trace of this cosmic magnetism, so we are left with a cosmic chicken and egg problem. Did the magnetic fields that guide star formation begin in the furious dawn of inflation, imprinted on the fabric of space itself? Or are they purely a later, local phenomenon, built from scratch in the furnaces of early galaxies? The answer would tell us if one of the most familiar forces in our daily lives is also a direct relic of the universe's most violent and creative moment, a ghost from the beginning that still guides the birth of stars. The search for primordial magnetism leads us to an even more exotic possibility, one that turns the faintest whispers of inflation into the darkest objects in the cosmos. Among the quantum seeds stretched by inflation, some may have been not just hills but mountains. The standard model of inflation produces beautifully small, Gaussian fluctuations, the gentle hills that became galaxies. But what if, in certain models, the inflattened fields rolled down its energy hill was not perfectly smooth? What if it experienced sharp turns, sudden plateaus, or moments of temporary acceleration? In such dramatic landscapes, the quantum fluctuations could become wildly amplified in rare, isolated patches. A region where the inflatten's energy density spiked could have been stretched into a cosmic scale over density of staggering proportions. When such a region re-entered the horizon after inflation ended, the sheer weight of its matter would have been catastrophic. Gravity would have won instantly. There would have been no time for a star to form, for gas to collapse gradually. Instead, that entire, enormous lump of primordial plasma would have collapsed directly under its own weight, punching a hole through the fabric of space-time itself. This is the birth of a primordial black hole, not from a dying star, but from a raw lump of the early universe. These would be black holes of almost any conceivable mass, from the size of an asteroid to thousands of times the mass of our Sun, all forged in the first second of time. Their existence would be a direct, unmediated product of the inflationary era's most violent imperfections. Today, these ancient objects would be drifting through the cosmos, silent and dark, their origin story written in their mass and abundance. This leads to two thrilling possibilities. First, they could solve one of cosmology's greatest puzzles. If a significant number of asteroid mass or planet mass primordial black holes were created, they could collectively form the mysterious dark matter that binds galaxies together. They would be the ultimate dark matter candidate, requiring no new fundamental particles, just gravity acting on relics from creation's first instant. Second, they could explain signals we are already detecting. When two such black holes spiral together and merge, they create ripples in space-time, gravitational waves. The LIGO and Virgo observatories have detected many mergers of black holes in a mass range that is surprisingly heavy for stellar origins. Could some of these be primordial black hole pairs, finding each other in the dark over billions of years? Their detection would be more than just finding another black hole. It would be opening a direct window into the physics of the inflation era. The mass of a primordial black hole is a frozen record of the size of the quantum fluctuation that spawned it. By measuring the population of these objects, we could essentially read the spectrum of the inflattened field's wildest fluctuations, testing models of its potential energy hill in a way the cosmic microwave background cannot. Finding them, however, is a monumental challenge. A lone, dark black hole is nearly invisible. Astronomers hunt for them using microlensing, watching for the brief brightening of a distant star as a black hole's gravity bends its light, or by searching for their influence on the earliest stars and the cosmic microwave background. It is a cosmic fishing expedition in the deepest, darkest sea, yet the potential reward is unparalleled. To hold a primordial black hole in our observations, even indirectly, would be to hold a piece of the universe as it was in that first trillionth of a second, a knot of space-time tied by the hand of inflation itself. The silent drift of primordial black holes through the cosmos is a haunting legacy, but it is a legacy we can potentially observe and measure. This brings us to a far more slippery challenge, a problem so deep it threatens to undermine the entire framework of eternal inflation. If our universe is just one bubble in an infinite, frothing multiverse, how can we ever make a definitive prediction about anything? This is the 24th mystery, the measure problem, and it represents a profound philosophical crisis at the heart of cosmology. The issue is one of infinite statistics. Eternal inflation, in its most straightforward form, produces not just a vast number of bubble universes, but an infinite number. Within that infinity, every possible outcome of physical laws, every conceivable arrangement of particles, every variation of history, must occur not just once, but an infinite number of times. This sounds like a powerful idea, but it creates a paralyzing paradox for making predictions. Imagine you want to ask a simple question, like what is the most likely value for the cosmological constant, or the details of the pattern in the cosmic microwave background. In an infinite multiverse, every possible value, every possible pattern exists somewhere. So how do you calculate the probability of what we should see in our particular bubble? You need a way to count the bubbles, to compare the infinite number of bubbles with one property to the infinite number with another. This is the measure problem. In mathematics, not all infinities are created equal. Some infinities are larger than others, but in eternal inflation, we lack a clear, unambiguous rule for how to perform this counting. Do we count bubbles by the time they were created, by their volume, by the number of observers inside them? Each choice of measure, each different counting rule, leads to wildly different predictions for what a typical observer like us should expect to see. For example, one measure might suggest that gigantic, empty bubbles that inflate for an extraordinarily long time dominate the multiverse by volume. In that case, we should be very surprised to find ourselves in a small, dense, structured bubble like ours. Another measure might suggest that bubbles producing the maximum number of observers are the most common. That could predict we should see physical constants fine-tuned for prolific star formation, not necessarily for our specific kind of life. The point is, without a unique and compelling principle to choose the right measure, the theory of eternal inflation loses its predictive power. It can explain anything because somewhere in the infinite ensemble there is a bubble that matches any observation we make. But a theory that can explain everything ultimately explains nothing. This creates a scientific and philosophical dilemma. Science advances by making testable predictions that can be proven wrong. If eternal inflation, through the measure problem, cannot make a unique prediction for our universe, does it cross the line from a physical theory into a metaphysical speculation? Some physicists argue that it does, that it surrenders the hard-won ground of empirical science. Others contend that the measure problem is simply a difficult technical hurdle within a profound new paradigm, one that future insights into quantum gravity may resolve. They believe we should not abandon a powerful idea just because its implications are dizzyingly vast. The crisis forces us to ask what we want from a theory of origins. Do we seek a single, elegant narrative that uniquely predicts our one universe? Or are we willing to accept that we live in a cosmos of stupefying plurality, where our local laws are just a random draw, and the ultimate theory describes a landscape of possibilities rather than a single reality? The measure problem is not a mystery about the early universe's physics, but a mystery about the nature of scientific explanation itself. It asks if there are realms of reality so expansive that they forever retreat from the grasp of prediction, leaving us to wonder if our most beautiful idea about creation might also be the one that places the ultimate answers forever beyond our horizon. The measure problem leaves us adrift in an ocean of infinities, wondering if any prediction is possible. Yet, one prediction seems to be writing itself across the sky right now, drawing a direct line from the universe's first whisper to its final silence. The same vacuum energy that may be a faded remnant of the inflation era's furious conclusion is now, 14 billion years later, gently pushing galaxies apart. This is the 25th and final mystery, a cosmic bookend that ties the ultimate fate of everything to its first fleeting instance. The story that began with an explosive stretching of space may end with a quiet, relentless thinning of all that it created. In the grandest symmetry imaginable, the Alpha and the Omega are linked by the same ghostly presence. Think back to the end of inflation, that moment of reheating. The inflattened field, having rolled down its energy hill, released all its stored power into the creation of the hot, dense plasma of the Big Bang. The vacuum energy that drove the expansion was supposed to vanish, to drop to zero. But what if it didn't quite reach zero? What if a tiny, irreducible fraction of that primordial energy remained, woven into the fabric of empty space itself? This faint echo, this cosmological constant, would have been utterly insignificant for most of cosmic history, completely overshadowed by the gravity of matter and radiation. For billions of years, the universe's expansion slowed under the pull of its own contents. But as the cosmos grew larger and more diffuse, the density of matter steadily dropped. There came a tipping point roughly 5 billion years ago when the constant, unchanging density of this vacuum energy finally became dominant. Its gentle, persistent push began to overcome gravity's weakening grip. The expansion of the universe started to accelerate. This is not just another chapter in the cosmic story, it is the final one. If this acceleration continues unchecked, as our best data suggests, the future it paints is one of profound isolation and darkness. Billions of years from now, the acceleration will have carried all other galaxies beyond our cosmic horizon. The night sky, currently sprinkled with the faint smudges of distant island universes, will go utterly black. Our own Milky Way will have long since merged with the Andromeda Galaxy, forming one giant, aging stellar system. But even that will not last. As expansion accelerates, the very fuel for star formation will be pulled apart. Galaxies will be stripped of their gas, and the last stars will eventually flicker out. Black holes will slowly evaporate over incomprehensible timescales via Hawking radiation. What remains will be a cosmos that is cold, dark, and almost perfectly empty, a near vacuum where particles are so far apart they may never interact again. This is the heat death, not with a bang, but with an endless, silent drift into maximum entropy. The haunting connection is this: the mechanism that set the stage for all structure, for all life, also encoded the instructions for its eventual erasure. The inflationary vacuum energy created the smooth, flat canvas. Its tiny remnant is now ensuring that canvas will be stretched into a featureless blank. The same physics that allowed for the glorious complexity of galaxies and stars contains the seed of their ultimate dissolution. This raises a chilling and beautiful question. Is this fate an inevitable consequence of how our particular bubble universe formed? In the landscape of eternal inflation, different bubbles could have different fates. Some might recollapse in a big crunch. Others might have a cosmological constant so large they ripped apart immediately in a big rip. Our bubble seems to have landed in a narrow window with just enough vacuum energy to allow for a long, fruitful period of structure formation before the acceleration takes over. We exist in the golden age, the cosmic afternoon between the fiery dawn and the eternal night. So when we look back to the mysteries of the inflation era, we are not just looking at our origin story. We are reading the first lines of our epitaph, the fine-tuning of the inflattened field, the quantum gravity conundrum, the nature of dark energy. They are all chapters in a single, continuous narrative that spans from the first trillionth of a second to the last star's final gasp. The universe's beginning and its end are not separate events. They are two expressions of the same underlying reality, a reality we are only beginning to decipher. The ultimate mystery is whether this story had to be told this way, or if, in the infinite froth of possibilities, we simply find ourselves in a tale that has both a magnificent middle and a quiet, inevitable end. We have journeyed through 25 mind-bending mysteries, from the first quantum nudge that triggered inflation to the haunting possibility of an infinite multiverse. We have seen how a fraction of a second set the density of every galaxy, the geometry of space itself, and even the ultimate fate of all that exists. The cosmic inflation era, though the briefest chapter in our cosmic story, is arguably the most important. It is the moment the rules were written, the canvas stretched, and the seeds for everything, from the largest supercluster to the atoms in your body, were sown into the fabric of reality. This era is not a distant, abstract concept. It is the foundational act of creation, the reason there is a there at all. each mystery we have explored, from the graceful exit to the ghostly inflattened field, from the cold spot to the measure problem, is a thread in this grand tapestry. They remind us that our universe is not a static place, but a dynamic, unfolding story, and we are privileged to live in the brief epoch where we can begin to read it. So we leave you with a question, one that now carries the weight of this entire cosmic detective story. Which of these 25 mysteries fascinates you the most? Is it the trigger of inflation, the quantum dice roll that became galaxies, or the chilling thought of eternal cosmic bubbles? Let us know in the comments below. Your curiosity is what drives this exploration forward. If you want to keep unraveling the secrets of the cosmos with us, be sure to like this video and subscribe. Together, we can continue to peer into the deepest mysteries of space and time, from the first whisper of inflation to the farthest reaches of the darkening sky. Thank you for watching.